Right. How are we going? All right. So if we can just take our seats, please, we'll get underway again. Gee, that's good. Oh. I'm getting a sense of importance here. I speak and it goes silent. That's unusual. All right, so I encourage anyone who's standing at the back who's wondering if there is a seat at the front. The answer is yes, of course. There's always seats at the front, so if you want a good view of the proceedings, please move to the front. We've got a fairly full session now through to lunch with 5 presentations to get through. The first I'm going to hand over to Les Brand. Les is going to give us an update on what his panel's been doing, but also a technology update as well. So I'll hand over to Les.
Alrighty, thanks David. Okay, so my name's Les Brand, I'm with Amplitude Consultants and I am the current, actually exiting convener of CIGRE A4, B4. So what do we do? The scope of SCB4, so the title of it is DC Systems and Power Electronics. And we'll just quickly go through the scope. So the scope covers high voltage direct current systems, power electronic devices, commonly known as FACS, flexible AC transmission systems. We also get involved in DC systems and equipment and power electronics for other applications such as distribution and power quality. DC and also DC converters for energy storage and for solar systems. We don't get involved in overhead lines and cables, and for Russell, we don't really care if they're overhead lines or cables. There's a general rule as to when you use one and when you use the other. Our members, we come from a good collection of manufacturers, utilities, transmission system operators, DSOs, TSOs, consultants and research institutes. And quite recently, like we used to be called HVDC and Power Electronics, and quite recently, I think Paris last year, we changed the name to DC, and a part of that is this drive to go into distribution systems. And you know, I have a view that at some point in time it'll be all DC. I don't know how many decades it's going to take to get there. But the logic is sound. We're generating in DC more and more, and we're consuming more and more in DC. So, and in my view, everyone's getting to a point where they've pretty much got an inverter in their house anyway. So let's do it. So in the Australian context, why do we care about these particular topics? First of all, Australia and New Zealand, maybe people know this, maybe you don't. We're actually, collectively, the two countries are very early adopters in HVDC technology. In New Zealand, the inter-island HVDC link was commissioned 1965, 1965. That was one of the first actual high voltage direct current systems in the world. That was a mercury arc valve, which later got upgraded to thyristors. Now, in Australia, we have 2 HVDC links that some people know about, some don't. Direct Link in New South Wales and Murray Link in Victoria, South Australia. Now, from a technology perspective, they're actually quite interesting because Direct Link was actually the first commercial VSC HVDC link. There was a smaller one in Sweden that was commissioned 2 or 3 months before, but that was, I consider that more of a research project more than anything. Whereas ours was actually an interconnector, and it was the first interconnector between New South Wales and Queensland for a very, very short period of time, until QNI came along. So Murray Link at the time was the longest underground cable in the world, and that's only recently been pipped from Southwest Link in Sweden, recently being a few years ago. And Basslink, of course, for a long time was the longest submarine cable in the world. Dangerously encroaching on Russell's territory right now. So just to make the point, though, that Australia has had quite a significant role in the early development of this technology. I will explain a little bit later in my presentation the difference between VSC and LCC, But suffice to say, VSC has only been around since 1997, and it is now more or less the standard, or the what would you call it, the industry standard for VSC, except for certain applications. It used to be the other way around. The other thing about Australia is we've been using fax devices on our transmission distribution network for a very long time. According to the database that our study committee has put together, I think our earliest one is 1977. And these devices, if you can see there, we currently have 65 currently in service around Australia and New Zealand. Far, in my view, outweighing many countries. And we can see that because whenever we report performance data and things like that to the CIGRE panels, Australia in this area is often the most major reporting entity. And then, of course, we all know about the drive for the connection of inverted connected generation, storage solutions, so they all have inverters in front of them. We're starting to experience issues. Not that B4 really has a lot to do with solving those issues. That's more the domain of other study committees. But in a speech in Johannesburg this year, I referred to us as the petri dish of the network, that we're actually experiencing and we're actually solving problems that other countries have not seen yet. And I'm sure some of the other conveners will talk a bit about that. So technical direction, what's been happening in the last 10 years in Study Committee B4? More application of VSC, I'll talk about that later in the presentation. There's this concept of HVDC grids, which you could look at as the first stage in the takeover of a complete DC transmission distribution network, but at the moment it's being driven by offshore wind. So there are some parts in the world, particularly around Germany, where there are a lot of offshore wind facilities some distance away from shore. And so they're now starting to think about, well, currently they're transmitting DC to the shore. Why don't they connect up in DC while they're out there and then have some kind of connection to the shore? So DC grids, and also Europe in general, there are a lot of HVDC connections in Europe. We're doing more and more power electronic applications as joint activities, so more with C6, for example, when we start looking at medium voltage direct current and the connection of batteries and so on. I've already talked about distribution and the fact we're going to take over the world. And items 5 and 6, fewer LCC working groups and more and fewer FACTS working groups. So it seems to be that generally we're starting to get towards, we're getting more interested in high voltage VSC applications and distribution solutions. So what are the drivers for that? One is offshore. One thing I really like about DC, if anyone asks me what I like about DC, I say there are two things. One is it's leading edge technology, and every project is different. Every project is bigger. It's a different application. It's a higher voltage. There's always something different about it. And the second is I get to show really, really cool photographs whenever I'm giving a presentation, which is always a plus. So, and then the use of PE in renewable energy. So working groups. We currently have 14 active working groups and we have 5 joint working groups. Most of them are on the topics of medium voltage direct current. Modelling is a big topic for us, and for those that work in the industry, the issue of models of inverters and things like that are issues that we usually tackle on a day-to-day basis. So here are a couple of working groups that are active. I just pulled out a subset, but some of them are quite interesting. Cyber asset management for HVDC systems is becoming something that everyone's getting interested in. If you can imagine, some of these HVDC projects are big, like massive amounts of megawatts, and if someone takes out one of those, they could actually do some serious damage. So there's a working group on that. Medium voltage direct current, HVDC breakers is another thing that everyone's looking at. and a few working groups on models. So what have we been doing globally? So globally, we've published a couple of technical brochures this year, one on modelling for harmonics, and the other is looking at harmonics for VSC HVDC. And there's been a paper from a task force. I think Graham explained what the difference, or Russell, the difference between a task force and a working group. We set up a task force trying to look at how we can make these HVDC converters behave like a synchronous generator. And it's the outcome was not very exciting, but it did come to a recommendation that there needs to be a working group on that. So there is actually a new working group starting this year on that topic, particularly how the converters can behave during an AC fault on the network. We publish green books. So this year we're publishing a green book on FACS, so SVCs, StatComs. These are nice fat books. They cost a bit of money. Usually they're up for sale at Paris 20, in this case 2020. And we also contributed to a green book on electricity supply of the future. David, do you know when that's coming out? No. I think it's going to be 2020. I think it's... Oh, okay. So it's going to be coming out later next year. And it's a pretty cool one because every single study committee has a chapter in there or a section in there. So it's a kind of encompasses the whole of CIGRE. A couple of working groups about to start. Open source, commissioning of FACS, and I already mentioned the AC fault response. And the other thing you may be interested in is we've been working on a HVDC compendium. So there are a lot of people starting to get interested in HVDC, and it would be good to have a better resource of list of HVDC projects than Wikipedia. Don't get me wrong, everyone uses Wikipedia right now if you want to know what's the biggest HVDC project. But this compendium is going to be available on CIGRE, and it's basically going to be available to all members, and you can download a couple of pages for each project. It gives you some basic parameters. Fair amount of work has gone into that. There's about 210 HVDC systems that will be represented here. Just quickly, I'll go through a few of the Australian contributions. So the Green Book on FACS, we actually had 4 members, Babak, Peter, Riza and Andrew, all contribute. So that was really good. I think for the size of our membership, I think we kind of punched above our weight on that one. So that was really, really good. I provided a contribution to the other Green Book. And the other thing that's happened is because of Australia's involvement in the early development of VSC, I've been asked to develop a document on terminology for VSC, which is a work in progress. We have quite a few people attending various working groups, as you can see there, in the task force and in the medium voltage DC, and a couple of the modelling ones. And next year I've been assigned the special reporter role at Paris. So this year's colloquium was in Johannesburg, working groups, tutorials. We combined it with the 9th CIGRE Southern Africa Regional Conference. So that was good. That made it quite a big event. And we got to meet lots of people from all over South Africa and some of the closer countries. 28 papers were presented, and all about all the stuff that HVDC gets involved in. We had our panel meeting last week, actually, 13 out of 19 members in attendance, so that was really good. A day and a half in Queenstown, half a day at Benmore. Okay, right. So I think I have 10 minutes. So I'm going to run through global trends in HVDC. So when I first put this presentation together, I came up with about 10 key points, and I've actually, given the time, I've crunched it down to about 5, right? So increase application of voltage source converter projects, but line commutated converter projects, LCCs, are not dead yet. They're just getting bigger and bigger and bigger, and I've got a few examples. Hybrid HVDC links, I'll explain that later. Earth return, all right, is Earth return completely finished? There are still projects that do Earth return, but there's been some interesting development out of China which could make it technically much better. Whether or not you can convince people who don't understand the technical bits is another story. And then global interconnections, Graham in his earlier presentation introduced that. So technologies, very quickly. Line commutated converters, we often refer to it as classic, utilises thyristor valves to commutate the current, been around since the 1950s. Thyristors have been used instead of mercury arc valves since 1972. And in the Australian context, New Zealand's Inter-Island and Basslink are both LCC converters. Second one is voltage source converters, uses transistors to switch the current. It is self-commutating. Now one of the impacts of the self-commutating converters is that we're not susceptible to commutation failures due to disturbances on the AC network like an LCC is. So that actually makes it more resilient to low system strength networks. And that's why it's starting to be used more and more in certain applications. It was first introduced commercially in 1997, and DirectLink was commissioned 2000. Just a quick one on the history of the development. You can see what's interesting here. Okay, the dashed line is when the new kid on the block turned up. We've got VSC, the first one in Australia. And then gradually the VSC projects just went up and up in voltage, often driven by the fact that up until recently, with the exception of one project that I can think of, VSC has been predominantly cable, so it's been driven by the development of the DC cable as well. So we started out as 80 kV, eventually became 200, we're at 320. Russell mentioned now that 650, 680 is now being introduced in the DC space. And as each VSC project has pretty much got bigger. So you can see the timeline there, and you kind of look at this area here. So DirectLink's down here, and it says 180. Murray Link is just behind it. And then there was kind of a period where there was only one vendor that was actually providing it. Suddenly a new vendor came in with a new technology called multi-level converters. Google it, it's quite interesting, and it's now the new standard. Oh. And then now we're up here. So there's a 2,000 megawatt, there are 1,400 megawatt converters now being built. I'll show you later, China's got some really big ones coming. So why? Why is VSC? One, it's a technology that's easily scalable, right? So you can use it for lower power applications, you can use it for really high power, or up to a limit so far. So as recently as 3-4 years ago, they built a 100 megawatt link to Åland, which is an island between Sweden and Finland. And of course, they're starting to use it for some offshore loads. And these loads tend to be quite small. So you've got you now have an option if you have an oil platform or some kind of platform some distance away from shore. And the picture that we've got there is Troll A off the coast of Norway. And that's 40 megawatts. So somewhere in there, so that's the actual platform, but somewhere right in the middle, they've actually built a VSC HVDC converter. So those applications still exist. Offshore generation, I already talked about. Interconnection into weak networks. So any application where you've got either you're connecting two weak networks or you've got a strong renewable energy source that you're feeding into a weak network, then VSC you'll find to be a little bit more robust, particularly less susceptible to AC network issues. And the other thing I really like about VSC, which would take a whole presentation on its own to explain why, but generally they have a smaller footprint. And the one thing that I can mention is that when you look at a LCC converter, the majority of the footprint is actually just AC filters, because you have to feed LCC with reactive power as well as control the harmonics. With the VSC, there's a good chance that you won't need any filtering. And this project that I'm showing just here, that's in San Francisco, just south of the AT&T Park where the San Francisco Giants play. It's in a very populated area, and it's quite a small footprint. That's a 400 megawatt converter. We didn't need any filtering on that converter, and that's why the footprint is so small. So you're looking at applications where you need to get a whole lot of power in to a very congested area. Okay, how am I doing? Right. Big projects, big VSC projects coming up. There's the 1400 megawatt between Norway and Great Britain. It will be the longest cable. It's 720 kilometres long. Interestingly, it uses a thing called a rigid bipole. And very quickly, a rigid bipole is where you get away with just two cables. You don't have an earth return, but you pretty much say, if we get a cable fault, that's it, we're out. But if you have a fault in the converter, one of the poles, it can switch over to the healthy pole. So it's kind of like halfway between a full bipole and a monopole. China, 5 gigawatts. So that's their impression of what the 5 gigawatt VSC converter station is going to look like when it's commissioned next year. And there's the Zhongbei 4-terminal HVDC link that are currently is in progress. Some of those converters are 3 gigawatts as well as it being a multi-terminal. So big LCC links, yes, long distance, large amounts of power. Why do they, apart from the fact that there's no 12 gigawatt VSCs right now, one of the main reasons for applying LCC, it's low losses and it's So low losses, it's proven technology at those kind of levels. And in this case, it's connected to a very strong network. It's like a hydro plant. So you don't have to worry about some of the things that for VSC. Oh, sorry, there was another thing. LCC is very good at managing the DC current during a fault. So whereas DC circuit breakers don't really exist, there are a few prototypes around and there are a few things being developed, but commercially they're not really available. So LCC links can help when you have an overhead line and you expect to get quite a lot of or a number of faults. The other thing about this project, it's 1.1 million volts, which is pretty awesome. The transformers are so big and the project is so big, they're building a factory at the site and they're bringing all the components in from Germany and Sweden and different places, and they're actually going to put it together, test it, commission it in this newly built factory, and when they're done and they roll off a few spares, presumably, that's it, they decommission the factory. So pretty big stuff. Hybrid, just quickly, hybrid basically means LCC at one end, VSC at the other. Again, China, for some reason they get to do this really cool stuff on their network and quite quickly. So this is a project that's currently underway. And don't ask me what WDD stands for, I don't know. But it's an 8 gigawatt rectifier with 3 and 5 gigawatt inverters. And the inverters are VSC. And why do you do it? Obviously, well, converters are more susceptible to commutation failures when they're an inverter. So you make the inverters VSC. Obviously, the LCC is connected to a very strong network, and you get the lower losses and the better fault handling capability of the LCC. So it's using the benefits of both and tackling the disadvantages of both at the same time. Could be the way of the future, who knows? And the other thing new about this particular project is it's using a combination of full bridge modules and half bridge. Just quickly, half bridge, you can't control the DC current during a fault. Full bridge, you can. They've worked out that all the modules don't need to be full bridge. The disadvantage of full bridge is it's twice the number of IGBTs than a half bridge, so it's more expensive and it'll have more losses. Deep well electrodes. Very quickly, China have put in these big 1,000 metre deep electrodes. The thing about earth return is that if you can place an electrode somewhere where you can force the current as deep as you can into the ground, then it won't have any impact on anything on the surface, whether it's a fence or a pipeline or the environment. However, we're kind of fast running out of areas to put these, and of course we have a lot of people object to that particular style. But these deep earth electrodes, they go down 1,000 metres and they just pump the current straight down. It'll mean that it'll have very minimal impact on the surrounding environment. So watch that space. That's a very new project, and some of us are getting quite excited about it, but we still have to change people's minds about Earth return. As you can see, when we start talking about global interconnections, getting an Earth return could be in the difference between a project happening or not, because the longer the cables get, if you can avoid a third cable, you can actually reduce the cost down to 40-50%. So global interconnections, Graham's already mentioned this, differences in time zones, solar, the light is, the sun sets at a different time to another country's peak. I think we all get the gist of that. Is it, what's that my sort of tip to, okay. So just a couple of examples. So CIGRE is really supporting this. Graham's mentioned there's a new technical brochure out, but there's a workshop that they're planning in 2020. It's going to be supported by a number of study committees. B4, of course, is a part of it. A couple of examples of these global interconnections. We've all heard about the Asean power grid. It's probably been around since mid-2000s, and it's changed form, but generally there's this overall drive in the Asean nations to connect all the countries together. And they're starting to pop up as individual projects, and some of these are AC and some of these are going to be DC. And then there's the Northeast Asia project, which they presented on in Johannesburg. It's a staged project, but I just thought I'd show you a graph for 2026, which shows Mongolia has a lot of renewable energy resources, wind and solar. So connection into Russia, connection through China into Japan, and I think South Korea is on that map too. Global interconnections. Sometimes it's a technical problem, sometimes it's not. It might be a geopolitical. And just quickly, I just want to throw up this slide. This is a project we're involved in, and I have the client's permission to present this information. So it's the Australia-Singapore Powerlink. You've probably seen a lot of it in the news. There's a lot of discussion on it. But from a technical perspective, it's a long-distance overhead line, and then it's a submarine cable that pops up through to Singapore. The Singapore link, 2.2 gigawatts, delivery of about 2 gigawatts, depending on what the losses end up like. Some deep areas. You could see here that we've got this kind of little single line diagram. Bit of battery storage at the source. The idea being that we can send solar power to Singapore, but we could also store it and send it to them sort of during the night. With an offtake in Darwin. And in this particular diagram, we've put TBAs to where all the battery storage are proposed to be located. Because it's a bit of a trade-off as to whether you transmit the power all that way just to be stored, or whether you store it at the source, and we still need to work that out. But it's a very exciting project. I think eventually Australia will be connected somewhere, so we just need to get it going. And we're very excited about this project. It'll end up producing 20% of Singapore's current annual demand, so it's a big amount of power. And what would it'll be technology-wise? It'll be a VSC technology, and it'll be multi-terminal. So there'll be a few firsts on this project, and yeah, it's very exciting. And a couple of pictures of the Ben Moore HVDC converter station at Transpower. So thank you for your time. That's all I got.